Hello and welcome back. I am Dr. Thierry de Vrijer and I will be your lecturer for part of this course. Before we look into different renewable energy technologies, let's define some basic connections between the three very important physical quantities: energy, force, and power. These connections are taken from classical mechanics but are generally valid. The learning objectives for this video are to understand how force, energy, and power are related. We will also learn to define and relate different types of energy and learn about the use of a number of alternative units of energy. We will start with the force. The force can be defined as any influence on an object that changes its motion. A force is exerted as a result of an interaction between two or more objects. The objects can be in physical contact or at a distance, like gravitational forces or magnetic forces. In this figure, a very strong man exerts a force on a granite block. The force causes the block to accelerate. According to Newton's second law, the acceleration a depends on the magnitude of the exerted force, F, and the mass of m of the object that undergoes the acceleration, as shown in this equation. We can gather from the figure that the force and acceleration are vectors, or directional quantities. The units of force are kilogram times meter per second squared, which is known as a Newton, denoted by capital N. The amount of energy used in this interaction is given by the product of the force and the distance s. Energy is a very useful concept to evaluate an amount of effort to accomplish a change in a system, or to put it simply, the ability of a system to do work. Let's put this definition of energy in practice. Here we have a tomato. We lift the tomato up to a height of 1 meter, for which we have to overcome the gravitational force G. Since the required amount of energy is equal to the force times the distance, it is equal to G times the height h. The gravitational force near the surface of the Earth is equal to the mass of the tomato times the gravitational acceleration, which is denoted by the lowercase g. The amount of energy required to lift a tomato is therefore equal to 1 kilogram times meter squared per second squared. This is known as a joule, after the English physicist James Prescott Joule. Since energy is equal to a force applied over a certain distance, 1 joule can also be defined as the amount of energy required to apply a force of 1 newton over a distance of 1 meter. We just defined energy as the ability to exert a force over a certain distance, but that is not the only definition of energy. Energy can be converted from one form to another, and all these manifestations of energy that we can observe are related through the great physical constants that define our universe. We have related energy to the mass of an object and the height of that object with respect to the surface of the Earth through the gravitational acceleration, which is derived from the gravitational constant. According to Einstein's famous equation, energy and mass are also interchangeable through the speed of light in vacuo, denoted by C0. The energy contained in a voltage, which is a difference in electric potential charge, is related through the elementary charge denoted by Q. The elementary charge is the charge of a single proton or electron, which have similar charge but are of opposite sign. The elementary charge is expressed in Coulomb, after French physicist Charles Augustin de Coulomb, which is equal to an ampere times a second. The amount of thermal energy present in a temperature is defined using Boltzmann constant, denoted by Kb. Finally, the discrete particles of energy contained in electromagnetic radiation, like light, is a function of only its frequency, denoted by h. Energy and frequency are related through Planck's constant. All these constants, and implicitly all these definitions of energy, play an important role in the field of photovoltaics. Now on to power. The power P is defined as the amount of energy used per unit time, denoted by T. Power is therefore expressed in joules per second. 1 joule per second is also known as a watt, after Scottish engineer James Watt. As an example, with 70 joules of energy, we could power this 70-watt incandescent light for exactly 1 second. We could also power this 7-watt LED light for 10 seconds, or 10 of these LED lights for 1 second. Joules are not the only unit used to express a certain amount of energy. 1 joule is a very small amount compared to the human energy consumption. Therefore, a different unit of energy is used for the production and consumption of electrical energy, namely the kilowatt hour. 1 kilowatt hour, as the name implies, is the amount of energy consumed if a power of 1 kilowatt is applied for 1 hour. Since 1 kilowatt is equal to 1000 joules per second, and there are 3600 seconds in an hour, 1 kilowatt hour is equal to 3.6 megajoules. The amounts of energy used in the atomic physics relevant for solar cells, on the other hand, are very small. We therefore use the unit electron volts. An electron volt is the amount of energy a body with a charge of 1 elementary charge gains or loses when it's moved across the electric potential difference of 1 volt. 1 electron volt is therefore equal to the elementary charge times 1 volt, which equals 1.6 times 10 to the power minus 19 joules. For the large-scale production and consumption of energy, a unit is used that is much larger than the joule, namely the ton of oil equivalent, or TOE. A TOE is defined as the amount of energy released by the burning of 1 ton of crude oil. 1 TOE is equal to 4.2 times 10 to the power 10 joules. Finally, in the food industry, the unit of calorie is used. 1 calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius at a pressure of 1 atmosphere. 1 calorie is equal to 4.2 joule. In summary, we defined the force as any influence on an object that changes its motion, and energy as the ability to apply force over a certain distance. Power is defined as the energy exerted per unit time. We introduced a number of alternative definitions, of which the kilowatt hour and electron volt are of special interest to us as solar cell engineers. In the next videos, we'll look at how different forms of energy are converted to electrical energy in different renewable energy technologies. So I'll see you again in the next video.